Actually put this in the beginning of the video. I'll record this so if Spencer wants to hear. So today is the 15th. Today we're going to cover sections 4.1 to 4.3 in Halliday. Okay, and we're going to hopefully start 4.4. I'm going to give you guys some one-dimensional kinematics free response examples to work on in the next couple days. I'm going to assign those today at the end of the period. As far as a due date, all this is on Moodle for due dates, but I'll tell you while we're here anyway. The free response, the one-dimensional free response questions are going to be due on the 21st by 8 a.m. Okay, on the 21st by 8 a.m. So that's not until, I think that's actually Monday. Yeah, I don't see you guys on Monday. If you ever see by 8 a.m. or by 3 p.m., it means it's a day that I don't see you. Okay, just keep that in mind. And I'm not doing this to give you more work. I'm trying to spread out your work a little bit more because I noticed last chapter I gave you guys major deadlines, and all those deadlines were when we had class. But I noticed that students had a tendency to think, oh, that means do it the night before. But it's not going to really work in this class, right? So if an assignment is due, I know that keeps happening. If an assignment is due on, say, the 22nd, don't wait till the 21st to start it. So I'm trying to give you guys intermediate deadlines that might be on days that we don't meet. It's for your own benefit. It's not to give you more work. Understand? Okay? Instead of making it all due on the day we have class, I'm picking days in between as well to kind of spread it out a little bit for you. So 4.1 to 4.3 today, and that's going to be looking at position, velocity, and acceleration in 2 dimensions with derivatives, with integrals. And then we're going to get into 4.4, which is projectile motion. That's going to be like the major focus of this chapter. Then on Friday of this week, I'm going to give you guys a quiz. I'm going to give you a quiz on Friday, and it's going to be a multiple choice quiz on 1D kinematics. So back to test 1, 1D kinematics, all multiple choice. That'll be on Friday. That quiz will only be like 10 minutes, and I'm going to give you about 10 questions. So you need to pace yourself wisely. And then we'll continue into 4.4 with projectile motion on Friday. Matt?
That includes and like dot product and
no product. Again, just kinematics, one-dimensional motion with multiple choice type questions. So they could be derivatives, they could be integration problems also now that you've covered that in this last section. They could involve things where vectors are given or where directionals are given in vector notation, but because it's one-dimensional, it won't matter that. You know what I'm saying? Yeah. So again, for the dot product and the cross product, all you want to know is how to compute the magnitude of that using AB sine C and AB cosine C. But that's not what this one is going to be. This is going to be one-dimensional kinematics. So using like your big 3 equations with acceleration, with constant velocity, but then also including slopes for derivatives and areas for integrals. Okay? I'm trying to give you guys just practice for quizzes also, and you get more grades as well to help out your test grades and also give you practice for the exam. That'll be this Friday. Then next week, the plan is to give you guys another quiz each day. I'll have you on Tuesday and Thursday next week. And that'll be like a 1D free response on Tuesday. Okay, so a one-dimensional kinematic, but a free response on Tuesday. And then on Thursday, I'll go to 2-dimensional, which is what we're kind of starting today, and that'll be back to multiple choice. Now, on those days, we're also going to work and do stuff after the quizzes. The quizzes will only be like 10 minutes to start. Okay, then we'll continue with section 4.4 on Tuesday. We'll probably do a lab on Thursday. Again, that's the 22nd and the 24th we're talking about. This is next week. I could even just like that. And then finally, the following week, we'll have the Tuesday and Thursday. Thursday, you already know, is your test. Keep in mind, guys, your test is on Halloween, October 31st. If I'm correct, you also have college deadlines around that time because that's November 1st, the day after. You also have, maybe some of you have an SAT the day after. So you need to start prioritizing. It means like if you're doing college applications the night before and you take the L on this test, I'm not going to feel any sympathy for you whatsoever. I know that college things are a lot, but you have time until that point. You need to space out every night, work on a college thing, get some of that done. Do not wait until the night before because then you're gonna screw yourself pretty much in the end. You're gonna be totally backloaded. And you guys know it's not just this class, but you're gonna have tests in your other classes around that time also. Right around the end of the quarter, you're gonna have tests in your other classes. Let's see. I'm gonna give you another quiz on October 29th. That'll be a 2D kinematic free response. Again, when I give you a free response, it'll be just one question. 15 minutes, one question. When I give you multiple choice, it'll be like 10 or 15 questions. Okay, that'll be again October 29th, 2-dimensional kinematics free response quiz. Okay, again, your test is 2 days after that. And that test will mainly be the end of chapter 2, that last section with integration and area and stuff. And then pretty much all of what we cover until that point in chapter 4, which will most likely be 4.1, 4.2, 4.3, 4.4. Okay, most likely. If we get a little faster, maybe we'll cover more. I don't think so at this point. We get beyond that. I already updated the problem set to include section 2.6, 4.1, 4.2, 4.3, 4.4. So you can see where that's listed as well. Okay, just so you guys have an idea. Again, a lot of the stuff I'm giving you involves a lot of work. Please space it out. Don't try and do all the assignments the night before. On the Moodle page, you'll also notice I put a lot of these due dates under homework, pretty much all the ones I just told you. I do not list quiz dates under homework ever. So if I'm talking about a quiz date and giving you a heads up ahead of time, definitely do what you're doing, which is writing it down. If you want to ask me about it, I'll reiterate it. But sometimes I do give pop quizzes, so it won't ever be posted on Moodle for that reason. But if I do mention it, jot it down. And then documents and handouts are where you'll find some more example problems for free response. Okay, I added those last night. So you'll see 1D and 2D free response examples. I give you a homework deadline for that as well, so you can look to see where that is. So take a look at your homework deadlines, and later today, make sure you start writing them all down in your agenda when you get a chance. Okay. I want to start chapter 4. I'm going to put up a multiple choice set for chapter 4 also. I'll put that on Moodle also like I did last time. I'm also going to put the chapter 4 notes, which are made by Halliday. That's on for chapter 2 and 3 already there. I'll add chapter 4 later today. Okay, you'll notice I also reorganized the Moodle page. I put a homework solution section. You should definitely utilize that when you're done with your homework. Like, what homework was due today for you guys? Yeah, what textbook section? 2.6, right? So what you'll notice is I just made 2.6 homework solutions available about 5 minutes ago. Okay, so under homework solutions, 2.6 should just be appearing now. So later tonight, what you really want to do is check through those problems. Okay, you should have already submitted them, obviously, but you're to check them over later tonight so that you can ask questions, I don't know, after school today or after school tomorrow. I know you guys don't have to be here tomorrow, but you probably should be to get some of your application stuff done. I wouldn't just sit home all day and do nothing. I would come in if it were me and get my application work done. I'll be here from like noon till about 4 with Science Olympiad in this room. So if you want to come by and ask some questions, I can give you some time. It might not be full attention at all times. It might be like I can give you an answer and come back to you and go back and forth, but to give you a heads up about that if you want to come by and ask questions. All right, with that said, let's jump into the section for chapter 4. So again, the plan for today is to get through at least 4.1 through 4.3. Based on how well we do in this part, we'll see if we can get to section 4.4. So, and again, as you guys know, I'm working out of the textbook when I use these numbers here. So 4.1 through 4.3 is very similar to what we saw already in the beginning of chapter 2. The main difference that we're going to notice here is that now we're looking at not just a simple derivative to go from position to velocity to acceleration, but we're looking at now if we have multiple dimensions. So let's start first with what we're going to call, in this circumstance, what we're going to call our position vectors. So position x, if you recall, we've been using a lot of x here, right, for position. When we think about this, with one-dimensional motion, it makes sense to call it x. With two-dimensional motion, it makes sense to call it y. With three-dimensional motion, it makes sense to call it z in the third dimension. What we're going to do today is specifically look at a vector r. And the vector r is really going to represent, what if we have all three of these motions together? Okay? And vector r is saying, if we have a position, that's a position in space, not just a position along an axis or on an xy plane, but what if it's in three-dimensional space? So if I wanted to designate, I can show you what I'm referring to again. I could say we had like something like 2i plus 3j minus 4k. And what this means is that we, on a Cartesian coordinate, okay, on a three-dimensional Cartesian coordinate, what we're doing really, again, is we're going over 2, right? That's from this 2. We're going up 3. That's from that 3. And then we're going back 4. And that's from the negative 4. So my position in space meets where those 3 intersections of planes would meet, really. And if you think about it, this is a plane cutting through 2. There's a plane cutting through 3. And then there's a third plane cutting through the negative 4. So it's tough to graph these. But just so you get an idea again, what we're doing, follow the cursor I'm showing here. We're going to go over 2. We're going to go up 3. And then we're going to go back 4. So in 3 dimensions, it's like somewhere around this area. But it's, again, hard to really show the third dimension with a coordinate. For the sake of this, I'm going to just generally guesstimate where it would look like it would be. So go over 2, up 3, and then it's hard to show the depth of 4. That's the one that's really hard to show. We have the depth of 4. So for the sake of the AP exam, though, luckily enough for you guys, you don't really have to worry about the third dimension. It's really only things in 2 dimensions still. So, although based on the class you were in last year in physics, you may or may not have covered a lot of projectile motion, some more, some than others, the idea is still that you're going to have 2-dimensional motion really for this test. So, although it is useful to recognize with vectors that we do have a third dimension, we're not really going to see much of that. Okay, now, Halliday uses a lot of stuff in 3 dimensions. We're going to really be simplifying things and looking at 2-dimensional stuff. And especially when we look at particles that are actually moving and we try to figure out, like, oh, where is it going to land? Is it going to reach this height later on? Or is it going to hit the ground before it reaches the foul pole? Or what is that called? The crossbar in football, the field goal post. So we're going to be looking at mainly things in 2 dimensions, but the third dimension exists, so you are aware of it. So you're aware of it. Now, based on the position function in 3 dimensions, we can also come up with a velocity function in 3 dimensions. And the velocity is simply the derivative of the position. Okay, again, it's the derivative of the position. Just like it was with 1-dimensional motion, it's the same concept. So when we start looking at this and we want to understand physically what's happening with this, we have to ask ourselves, we just have to take the derivative with each component. So really what we're doing is if we want the velocity, we can say v, which is really equal to dr dt. It's the derivative of the position vector here. So what does that mean? It means simply I'm taking the derivative of each part. Now, these are all constants, so obviously those are positions. They're not going to get a derivative from them. Right? They're just going to become zeros if you were to do it. But generally speaking, it looks like this now. dx dti plus dy dt j plus dz dt k. And just ask yourself the question, well, what does dx mean? The derivative of the position with respect to time. The derivative of the y position with respect to time. The derivative of the z position with respect to time. So all we're doing is taking a derivative 3 times. It's no different than what we did. The notation looks so overwhelming when you look at this. Like, oh my gosh, I don't even know what this means. But really, it simply means when you want velocity, take the derivative 3 times, or just get the velocity in each direction. Okay? So those are equivalent. I can write it like this with all my Vx, Vy, and Vz with ijk, or I can write it as dx dt, Vy dt, Vz dt. Okay, I can write it either way, but I want you to recognize that if I were to, and then we're going to do an example in a minute, you'll see this. If you're going to be given something that is a function in this case, a function of time, we can take the derivative of each piece. Remember, 2, 3, 4, these are not functions of time. God bless you. This is a specific position in space. So getting its derivative is not going to help us at all right now because, again, it's a position. It's a position. When we have something that has t in it, then we can take the derivative and actually get the velocity.
So where does t come? Where did t come from?
Where? Were you here? Give me like, I don't know, 30 seconds and let me get to that and I'll show you. I'm going to go through an example of where t is going to come into play a role. Okay, but I'm giving you the general nomenclature so far, the general arrangement that we're going to be using. Acceleration is very much the same idea. So acceleration vector is really going to be the derivative of the velocity vector with respect to time. So again, it'd be dv x dt I plus dvy dt j plus dvz dt k. So again, to get the acceleration, what are we saying? Just take the derivative of velocity, but each of these three parts of the vector separately. So let me jump into an example so you can see this, because right now it's probably a little bit confusing as to what we're even doing here. Okay, so I'm going to start with an example. This example, just so you're aware, starts on page 63. Okay, it starts on page 63. Okay. I know people are still writing, so I don't want to lose this material. So I'm going to move it over for now so you can still see it. And let's start an example here. So here's what the example says. A rabbit runs across a parking lot on which a set of coordinate axes has, strangely enough, been drawn, meaning you superimpose them on the parking lot. The coordinates in meters of the rabbit's position as a function of time in seconds are given by the following. So we're given the following information. We're given x as negative 0.31 t squared plus 7.2t plus 28. And given the y value as 0.22 t squared minus 9.1 t plus 30. So we're given the rabbit's position as a function of x and y. How come not z? Well, why didn't we have a z direction here? For rabbits running along a parking lot, how come we didn't have a z direction, Chris? Yeah, it's not moving off the ground into the third dimension, or it's not burrowing underneath something. But you could, theoretically, have a rabbit that burrows underground to get under fences, which is what rabbits do, right? Or levitate somehow. So for now, though, we'll say z is not a problem here. We're not worried about the third dimension. So Tristan, to answer your question already about where's time going to play a role. So our x and our y components are going to be written this way. So if I wanted to write the position vector, instead of a 2 here, see this 2 on the left? This 2 becomes that entire equation. This 3 here becomes this entire equation, the entire right-hand side. So remember, this is a specific position or a moment in time that I gave you to start. This is now the position of the bunny as a function of time.
Oh, so to find like the velocity, you would add the two derivatives?
We have to take the derivatives and take a look at those. We're going to get into that for sure. Yep. We have to take separate derivatives though. Matt.
So like I, J, K, that's just kind of like a verbal way of saying it's like 2x, 3y, 4.
Same as when we learned vectors the first day of the
so
year.
that's just
Exact same thing. Yep.
And once you bring the velocity, like how, like what, I'm kind of confused how that transition's made. Like,
So the velocity becomes the derivative of the position function, which is what it's showing here. So the derivative of position is vx, the derivative of position of y is vy, the derivative of position is vz.
oh,
But
so
then when you
velocity
walk-
is just finding the derivatives of both of those and adding them?
Correct.
Oh, okay.
Yeah, adding them with their respective values. So
Yeah.
let's start by writing the position function for this. So the position function, as seemingly simple as it is, we're going to write, becomes the following. R equals, and again, it's literally the same thing. And I know this sounds trivial, but I want you to see it. And I'm literally just copying the exact same two things down I had above a moment ago. And I'm tacking on the I or the J to represent whether the X or Y direction I'm really looking at. So again, this is the position in the X direction, this is the position in the Y. I ran out of room, or else I would have not put it below, okay? And normally we put this to the right and continue the entire thing. You see what I'm saying, everybody? This would normally be over here. I'm just running out of room, that's why it's not there. So that's the position of the rabbit at any moment in time. So you want to visualize this as an XY plane. So let's say, for example, and maybe calculators out for this. This would be really helpful, by the way. That's another thing to point out. I mentioned it already once. I'll say it again. When you have a calculator, use it in this class, right? Use it as much as you can on tests. Use it as much as you can on the AP exam. You got to show your integral or show your derivative work to start, but then doing the work, evaluating functions, use your calculator. So personally, I'm about to ask you to find a position at 5 different time periods. Or 5 different, not periods, but 5 different moments or instances. So does it make sense to calculate this 5 times here and then 5 times here? It probably doesn't. So does somebody have a recommendation of how we can use maybe our calculator to help us here, man?
You can plug in once and then just put like kind of like replace the variable with the number each time you just repeat the equation.
So that saves us time, but there's an even faster way. I like what you're saying. You can put in the home screen and press second enter and
You can
replace
put
it.
into the graph.
Yeah, so what should we do specifically, not just the graph? Tell me more.
Oh, you go to like the calculate section and then you just enter the value at each.
Okay, that'll work. You're better than that. You're better than that.
You go to table. And then
I would use the table. So, because the table you can specifically type in the times. I'm going to show you to do that. So while you're waiting, I'm about to get my emulator up so you can see it. Please put this in y1, put this in y2. Put them in separate y equations. Put one of them in y1, put the other one in y2. Remember, y1 and y2 are just names the calculator gives it. It's not necessarily the actual right names. You follow me? Okay, it's not actually what we're doing. It's not really like we're calculating the vertical height in the calculator. Just call one of them y1 and the other y2. Tell me I don't have this calculator anymore. I have to have it somewhere. Now, once you're in y1 and y2, what you can do is you can go press second and then go to your table settings. I'm trying to pull up my emulator, guys. I just don't seem to have this for some reason. Second, and then go to table settings, please. Here it is. Got it. Okay, give me 1 sec, and I'll put it up so you guys can see us better. God bless.
Thank you.
Okay. So I'm using the 83, which is the same as the 84. If you're using the 84, that's fine. If you're using something else, I honestly can't help you right now, and it's just going to take too much time. So you're going to have to figure this stuff out on your own if you're using a different type of calculator. So we're going to go to y1. We're going to clear it out. We're going to put in what we had here, which is going to be 0.31. Now, I don't have t on the calculator, right? But we know by now, I hope, that x, t, theta, n stands for? More generally, the value that is called the what variable? Independent, that's it. The independent variable, whatever, the horizontal variable. Thank you. And this is another good feature, second insert. If you haven't used this by now, you can insert a value in between stuff. Okay, there's a lot of calculator like things that they save a lot of time. And I got to make this squared, right? So I got to insert a squared here, second insert, and I want to square that. Then it's 7.2x plus, oops, plus doesn't work on the keyboard apparently, plus 28. Okay, so that's y1, and that's really my x position at any moment. And then in y2, I'm going to put the y position, 0.22 x squared. This is going to be minus 9.1 x, and then finally plus 30. Now, again, I press second, I go to table settings. Change independent to ask. This is the key, and everyone leaves it on auto pretty much all their high school career. I don't know why students don't use this feature enough. What it does, again, press second, table settings, which is the window key. Okay? Then change independent to ask, and hit enter on ask. Now what it does is it allows you to physically ask the calculator the independent variable, and it spits out the dependent variable. So if I go to table now, press second and then graph to open up your table, what you'll notice, first of all, let me delete these. What you'll notice on yours most likely is that you have an empty table. You should all have empty tables unless you've done this, what I'm doing already. Now what I can do is I can say the following. And on this problem, here what we're going to do. We're going to plot, so I'm going back to the thing. We're going to plot the position at 5 different instances. Let's do times equal to the following. Let me think actually before I actually give you the number, if I want to use the right value. Let's do time equals 0, 5, 10, 15, 20, 25.
10, 15.
So 0 to 25 increments of 5. Now, when that happens is actually, you can leave it on auto, but I'll show you that whole feature in a minute. So we want those 5 time periods. We want the position at those 5 time periods. So what we're going to do instead here is we're going to use our calculator to do that. So we're going to type in directly here. 0. Oops. I'm on the second. There we go. 0, enter. 5, enter. 10, enter. 15, 20, and 25. So I don't want to have to do a lot of work, and especially on an exam like this, to save yourself time, you want to consider the fact that your x and your y values can be calculated nice and quick. So the x value or the position changes. It goes up, it goes up, it goes up to about 69, then it goes down. The y position gets, well, it starts at 30, it becomes more negative, more negative, more negative until negative 64, and then it starts to become less negative and it goes to negative 60. So what we recognize here is that this this rabbit we're looking at here, changes its position, x and y, and it's all according to this equation right here. Now, what does that look like graphically? If we're going to graph this to physically see the position, this is what it looks like. Those data points that we just did right there. So what was the first y1, y2? So what was the x position, comma, y position at time equals 0? What was it?
30.
20, comma, 30?
28, comma 30.
28, comma, 30. So take a look. Over 28, up 30. This is not plotting versus time. You see the difference? This is the y location and the x location. This is the, what is it, a parking lot? Whatever. This is the parking lot itself. So at 0 seconds, this is where the bunny is. Then after 5 seconds, what became your x and y position?
56.25, comma, negative 10.
56.25, here it is, comma, negative 10. There it is, and that's after 5 seconds. So what we're doing is we're setting up really a parametric function is what this is called. It's called a parametric, that's not actually important. No, right? The idea, sorry, but you're going to use that word later in that's why I use these vocabs so you can hear them. But this is the second instant in time that we're looking at. This is the third instant, and it should be near 70, comma, negative 40. Around there?
69, negative 30.
69, negative 39. Around 70, negative 40. And again, we plot all these positions. So it looks like this bunny is moving in some sort of a curved path, right? Some sort of a curved path. So its position is clearly changing. Does that make sense so far what we've done for the position function? So a position function in 2 dimensions is not always going to be drawn as a position time graph. You see what I'm saying? In the past, it's been a position time graph for 1-dimensional motion. But for 2-dimensional motion here, we can graph y versus x, and that gives us more information than position versus time for the y, and position versus time for the x separately. Now, this problem also asks us to calculate, I think it's position at given, It says at time equals 15 seconds, calculate the position. That was the original question. I had you guys do it for all those times. Okay, so at 15 seconds, though, again, what would you do? You plug a 15 into your x equation, which is right here. You plug a 15 into your y equation right here, and that's what gives you 66, comma, negative 57, which is this coordinate right here, showing up at 15 seconds down there. Okay? So that's the idea from 4.1 about position. Chip.
This might be a really bad
No,
question,
okay.
but like, why are we doing x versus y as opposed to like x versus z? Because isn't y like up? And
Yeah,
x
but
and z
remember,
is
it's all arbitrary, Chip. So if I call the xy plane the ground, then z is up. If I call the xy plane the board, then z is out.
okay.
Right? Think about it. I can call down negative. I mean, have you done this ever in physics last year? You can call down negative if you want to all year. My AP physics teacher, so we had AP B and an AP C. The second year of AP physics, he actually started the year by calling everything down negative, just to mess with us for like a week. And it actually, I mean, in the end of things, it really doesn't matter, I guess, but it just gives you a different interpretation of stuff. So everything's arbitrary, right? Like if I'm calling that north in the city, that's fine. But on a piece of paper, we usually call up north, right? But your paper might be oriented that way, and that's clearly not north in the city. So it's all a function of what you call east, west, north, south, up, down, okay? So in this case, in this circumstance, because the bunny is only moving along a along one plane, not into the third dimension, it just makes sense to call that plane xy. But yes, you could call that xz or yz, whichever you'd like to. Okay? All right, let's go back to the notes. So that's what I want you guys to gain from the information so far. Now, the second piece I want you to gain from 4.1 is we could also calculate the angle at any moment that the object or the bunny is. So let's go back to this diagram so you can see it. So we could also calculate the angle that it makes when it moves. So in this case, what they're doing is they're calculating the angle with respect to the origin to the time when it's at 15 seconds. And this being 41 degrees, coming from, again, opposite over adjacent. Okay, you're going to use that a lot this year. You've used it already. The tangent inverse. Okay, the tangent inverse is very, very important when it comes to figuring out angles. So we're going to continue to use that. And that's what they're doing by giving you the 41 degrees there. Again, that's at the moment at 15 seconds has elapsed. So after 15 seconds has elapsed, compared to being at the origin, where is this vector's orientation is what it's asking. Go for it, yeah.
Wait, is that, so is, in reference to which axis? Like which?
In reference to the origin with respect to the x-axis.
Okay.
Yep, that's a great question. So it's southeast, Karen. Southeast. Yep. Now, here's the other thing. If I wanted to know the direction of the vector from time equals 0 to time equals 15, we can all see for a moment how this changes. Take a look at this graph, what it looks like now. I wish Spencer was here today. He's going back and forth. He's going to be missing a lot. It's not on the recording. The recording is only what's on the iPad. So if I wanted to go from time equals 0, which is here, to time equals 15, which is here, now, if I were to look at that, now I've got a new reference line. And my angle there would be different than with respect to the origin.
So wait, why would you?
So if we want to know from where the bunny started to time
that's
equals
T0.
15 seconds, that's D0 up there, and we want to know the overall displacement, right? We're going to need to know this length of this vector r right there, and we're going to need to know that angle theta right there.
So wait, how would you? Where would the components?
So what we'd have is this. Well, we'd have to do some math, right? So what is this value? This is the vertical, that's the horizontal. So we'd have to figure out, which we have in our data from your tables right now in your calculator. You've got the x position at time equals 0, and you've got the x position at time equals 15. Subtract those x positions to see how far the rabbit traveled in the x. So what do you get when you do that? When you subtract your x position at 15 and at 0, what do you get from those? What do the numbers give you? You guys have a calculator in front of you so we can do it for the numbers. What's the position? Or give me the positions at least so I can label them too. Maybe that'll help.
At 15,
Sure.
it's 69, negative 39.
And at 0, what was the position?
28, 30.
20, 30?
28,
So really, we're going to do 69 minus 28 to get the x displacement. And that's going to give us this number up here, which is going to be 41.
That's not the right.
Is that not the right number?
30,
For
28.
15.
That's for 10. It's 30, 28, right?
What's
No,
this?
that one, yeah, it's 66.25, comma, negative 57.
Okay. Thanks for the correction. That's all right, guys. Just check your work. So, and that makes sense actually, based on where it is.
Yeah.
So 66.25 minus 28. We're gonna get what? 8.25 going back to 38. Going back to 58. 38.25.
Yeah.
And then the y direction, we're gonna get 87.
Yeah.
Remember? Taking a look to see how this length is. This is 30 above, this is 57 below. So if I want to figure out what r is, I could say that r is equal to the square root of 38.25 squared plus 87 squared. And theta is equal to the tangent inverse of 87 over 38.25. And those are going to be my two answers that I'm going to get from this. Again, what I want you to recognize in this case is that the position of the bunny in the x and the y direction changes. In both the x and the y direction changes. Let me actually do the same thing you. Okay. All right, just so he can see what we drew on the board. But again, this is out of your text in page 64. Okay, so that's what I want you to get at for the position part of this. Now let's move on to the next part. Okay, let's move on to the next part. Let's take a look at velocity. We're going to use the same function. So I started a new page just now, but you guys can keep the same function open for now. So using the function for r that we just wrote down, all we want to do is practice the concept of average versus instantaneous velocity. So the r function, you have the first part, I, plus the second part, j. Again, this is the same as the last problem. Negative 0.31 t squared plus 7.2 t plus 28. And then on the other part, 0.22 t squared minus 9.1 t plus 30. Now, given that position function, if we wanted to calculate the average, listen carefully, the average velocity between time equals 10 and time equals 20, how would we go about doing it? If I want the velocity from t equals 10 to t equals 20, and again, average, I'm putting the key is average, I'm stating the word average, right? And it's a time period that's elapsed. So if I want average velocity, Chip, what am I going to do here?
And you take the x coordinates and divide them by 2.
Where's the 2 coming from?
Because you have two different time values.
What's the definition of velocity, though? What is its definition?
Be over 10 then, because it's over 10 seconds.
Good. It's over time, right?
Yeah.
So if I want to find the average velocity, I can find the change over the time period, just like we did for one-dimensional. If I know I walk 5 feet over 5 seconds, my velocity is 1 foot per second. 5 divided by 5. So the question really becomes, how much does our x component change from 10 to 20 seconds? Then how much does our y component change from 10 to 20 seconds? Now, luckily enough, because you put this in your data table already in your calculator, you all can give me the numbers like this. So tell me, please, what is the position function at 10 seconds? What is the position function at 10 seconds? What are the values? 69i, go ahead. Minus
39.
All right. And what's the position function, or what's the location, I should say, not even function. What's the location at 20 seconds according to your data table?
48 negative 64.
48i minus 64j. All right. So we've got the position at 10 and at 20 seconds, right? That's a 10, by the way. We've got the position at 10 and 20 seconds right now. So as a result, if we want to figure out the average velocity, we can see how much it changes. So again, it's final minus initial over the time period of 10. Final minus initial over the time period of 10. And notice what I'm doing. I'm really leading you guys into the first step to recognize that position, velocity, and acceleration can all be worked out independently along each axis. You can look at your x's separately, forget these are here. Look at your y's separately, and forget those are there. And do the problem literally twice. So when I want to figure out the velocity on average, I would say in this case that it would be, again, final minus initial over time period elapsed in the I direction, and then final minus initial over the time period elapsed in the j direction. Yeah, they're going to get numbers, obviously. We're going to get values, you're going to divide by 10 with the decimal spot. But the idea is what I want you to see. Final minus initial, all over the time period elapsed. Remember, 10 is not the starting time. Maybe I should, whatever, I already used these numbers. But from 10 to 20, we got to recognize that delta t equals 10. That's the value that's going in there and down there. Okay, it's the time period that's being used. That.
How come you couldn't find R10, R20, and then use those as the top values?
And use those as your what?
The top values. So if I could do 69 minus 39, I'm sorry, 49 minus 64 minus 69 minus 30 over 10, and instead of like separating. Like, are you?
Well, this is x. This is the x position. This is the new x position, right?
Mm-hmm.
So we want to find out the velocity for the x first, put it next to I, then find out the velocity for the y direction, put it next to j. So I can't just subtract these two and put it over 10. Because remember, this is its position traveled in the x, this is the position traveled in the y. We're doing them independently. Remember the first day of class this year, I had that little car come out, and I had to move, and we tried to see if the marble would land back in every time it was launched out? Remember that first day? That whole concept is where this is coming from. The directions are treated independently. You want to look at your x as its own portion. Look at the y as its own. Look at the z as its own. The overlapping variable will be what? That's the one variable that's going to overlap amongst the x, y, and z. Time. Time is the variable that is going to be incorporated in all three. But the x direction could have different velocity and different acceleration than the y direction. And that's completely okay. And that's where projectile motion comes in. Right? When I throw a projectile across the room, the acceleration it feels is mainly gravity acting down. That's a y acceleration. It doesn't have much x acceleration. It has a little air resistance we'll talk about, but really not much. So we need to treat these directions independently from each other.
Wait, so the constants or the positions, they do difference in positions or difference in time?
Correct. This is change in position over time. Change in position over time, which is the definition of velocity. Absolutely right. All right. Now, if we did not want the average velocity, but we wanted to know the instantaneous velocity at a given moment. Oops. Still on the screen, good. At a given moment. So let's want the velocity vector at 17 seconds. If I want the actual velocity at 17 seconds, not the velocity between two times, not the average velocity, but the velocity at a moment.
We should do the derivatives of
Good.
the two equations over there and then just find the magnitude.
Precisely. So tell me what the general velocity function would look like based on derivatives. What would the general velocity function look like based on the derivatives up there? Chip, head.
Negative 0.62 t plus 7.2, like in parentheses I, and then plus 0.44 t minus 9.1 close paren j.
Nice. Okay, so that's the general velocity function. All Chip did was use the power rule, right? He used the power rule on the x component and on the y component, but he used it 2 times on each, and obviously your constants drop off. Okay, that's the velocity function as a whole. So if we want to find the velocity at a given instant, that's when this will be used. That's when this will be used. We will not use this velocity function to find the average velocity between 2 time periods, because that's not what it's for. This velocity function is to give you the velocity at a specific moment. At a specific moment. That's what this velocity function is used for. So when we want to figure out the velocity at 17 seconds, we simply plug in 17. So it's going to look like negative 0.62 times 17 plus, I'm running out of space, bear with me, plus 7.2, and that's in the I direction, plus in the J direction, 0.44 times 17, oops, minus, not plus, minus 9.1 in the J. What does that become? Negative 0.62 times 17 plus 7.2. What do we get for the I component? Thank you for those who are actually doing it. M?
Negative 3.34.
Okay, and somebody else for the J component, for the J.
Negative 1.62 J.
Thank you. And what would my units be for this entire thing? What would my units be? Meters per second. I can do that at the end to make it easier instead of writing meters per second a couple times. So what is this problem getting at? Well, the idea is that if I want to know the velocity at any given moment, just like we did with 1D kinematics, take the derivative. Just the same thing. So on test 1, a couple of you guys struggled, or a couple of you all, not guys, you all struggled with this idea of remembering when to take the derivative, right? The derivative is useful when you're looking for velocity at a moment, or acceleration at an instant. So that's why we did the derivative on the right side over here. But on the left side, instead, we found the average velocity. Okay, so if you want to write yourself a little note at the top of each spot, write it down. So you might want to write instantaneous for one and average for the other, right?
Where did you find those values to take the derivative of? Sorry. Is it just that?
It came from the position function. Remember, the derivative of the position function is going to be your velocity function.
Right.
Okay, so this was average velocity from 10 to 20. This was the instantaneous velocity at 17 seconds. Now, can somebody help me with this next part? What's the speed? What is the speed at 17 seconds? What would the speed be? Yeah.
The absolute value of the velocity.
Give me more than that, because I have two velocities here, right? So if I want to know the overall speed, I've got two velocity components. I want just the overall speed. Max.
I just use the Pythagorean theorem.
Yeah, that would be Pythagorean theorem again. So you could absolute value of each to start it, but the idea to get speed or to get the overall velocity in this case, or speed, we want to think about the Pythagorean theorem. So what is this really telling me? Here's what this is telling me. Let's say this is my projectile. It says that it's partially moving left because of the negative 3.34. It's partially moving down because of the negative 1.62. So my overall velocity or speed in this case is going to be this hypotenuse of the triangle. So we've got a triangle here that gives us the x and the y components of velocity. We're going to have to use Pythagorean theorem to get the overall velocity, and then, as Matt said, we're going to take the absolute value, but not until that moment are we going to do that. So we're going to have, again, 3.34 and 1.62. 3.34 squared plus 1.62 squared. Enter. Square root, second answer. All right, square root, second answer. What do we get for our overall velocity? 3.7. And how about an angle? How about an angle? Remember, tan inverse of 1.62 over 3.34. In degree mode right now, right? In degree mode right now for sure.
Would you put them in negative?
No, because what we notice, so first of all, you can, but I don't do it because I use my diagram to indicate my directional. Like, I know this is southwest because I'm going west and I'm going south of that. Because both of these are negative, I'm also going west and south. So I know it's southwest, so I never use the negatives. I use the absolute value of those quantities. What do you end up getting for theta?
25.9.
So that's my velocity vector right there, which is really the same thing as this right here. They're actually the same thing. Okay, this is technically, remember at the beginning of the year I said to you guys we're going to use polar coordinates? This is actually polar coordinates. This is giving you a vector length and an angle. That's what polar coordinates are at the bottom. Up here, these are Cartesian coordinates, x and y. Okay, x and y. But again, we're going left and down from both negative signs.
I was just gonna ask how you found the angle, not just the surface of it.
I use tan inverse of the y over the x always, because it's always going to be this angle, and it's always going to be opposite as y and adjacent as x.
Okay.
So you could write SOHCAHTOA out every time, and you could figure it out every time, but it will always be tan inverse of the y component over the x component. It's never going to change. Now, if you need to give this angle right here, Matt, then you can just subtract the answer you get from 90. It makes it a lot easier instead of doing the tan inverse of x over y. That's what that would really be. Okay? But I would always do tan inverse of y over x to get the angle with respect to the nearest x-axis. Again, the idea behind this is that you are going to have two different moments where you might calculate velocity, once as an average and once as instantaneous. Okay, the average being two time periods, we're going to physically find the positions and divide by time, or the change in positions and divide by time. Here, you can't do that. Okay, again, because the time period is so small, you can't divide by time. Let's now carry this into the next part. What do you think we're going to do after this? We're going to look at acceleration. So let's take the same function here. So we're going to now have, let's see, I'm going to put it on the bottom so there's a little bit of room here. So I'm going to put acceleration down here now. And instead of starting back over with the position function and taking its derivative twice, instead I'm going to do what, Tristan?
It would just be 0.62 I and negative 0.62 I and 0.44 J.
And that's in meters per second squared. Okay? So again, it's a constant now, the acceleration. It is not a function of time. It is not a function of time. What if I wanted to do the exact same process all over again? It's annoying, right? What if I did? What if I wanted to find the average acceleration at 20? What if I wanted to find the instantaneous acceleration at 17? Give me some information, Matt. What do you think?
Wouldn't it be the same? Because
What do you mean?
the acceleration would be the same always because it's constant, it's not changing.
What would be the same? The average or the instantaneous?
The instantaneous.
The instantaneous would definitely be the same the whole time, right? We could all, so we think about this logically. If I want the acceleration at time equals 2, where can I plug in a 2? Can I plug it anywhere?
No.
Is there a t anywhere? So that means that the acceleration is absolutely constant. So at any instant in time, the acceleration is going to be the same. Now, what about the average acceleration throughout the entire time period? We could figure it out, right? We could do it, right? We could take our velocity function, which is right here at the top, plug in 10 and then plug in 20 for each of those, subtract them, divide by the total of 10 seconds, kind of like we did here. Right? We would do this entire thing again, but instead it would be acceleration. What would happen? What would happen, Chris? Would be what? Not undefined. Not undefined. It would still be the same as this. Whenever something is constant, its instantaneous value at any moment is the same, so is its average value at any moment. So theoretically, could you find average acceleration in another problem? Yes. You would do exactly what you did here. So we'll jot it down. But in this problem, there's no need to do it, but just to write it down. If you want the average acceleration, you would again do what we did earlier for the average velocity. You would take the velocity at 20 seconds minus the velocity at 10 all over the time period of 20 minus 10. And this would be for the x first. And then next to that, you would do the velocity at 20 in the y direction minus the velocity at 10 in the y direction all over again, 10 from 20 or 20 minus 10. So this problem is the same as up here. I'm going to put a red arrow so you can see what I'm referring to right now. It's the exact same approach we took up there. When we wanted average velocity, we looked at the change in position over time. When we want average acceleration, we look at the change in velocity over time. But, as Max mentioned, if we do this math, go ahead and do it if you want. You're going to get this answer will definitely be negative 0.62. And this answer, when you do this math, will definitely be 0.44.
So it was like a cubed function.
Very good. That was going to be my next question, Tristan. Well, way to think ahead. If it were a function that was not simply squared, where the second derivative becomes a constant, what if it were cubed? You would have to do something like this. Or what if it were a sine function or a cosine, which you're going to learn a little bit later, and we'll come back to this idea, and you'll see it again. Well, that you would, for a sine or cosine function, you could take infinitely many derivatives. Kind of cool, actually. When you get to that, you'll see why. But for a sine or a cosine or a trig function, you could take derivative after derivative. It's never going to run out of derivatives. Whereas for a polynomial function, but we already noticed, right? The minute we take two derivatives of quadratic, we are left with a constant. What's the derivative of a constant? So the third derivative would be 0. The fourth derivative would be 0. The fifth derivative would be 0. You follow? So I can't keep taking derivatives of this function because it runs out with the power rule. You keep running down power over time. But with a sine or cosine, you can take it infinitely many times. I'm not going to get into why that is just yet, but you're going to see that in your calculus course. Let me see if I want to add anything else for this rabbit problem real quick. Oh, how would I find my overall acceleration as a vector with a magnitude and a direction? Just like we found the overall velocity in the top right up there. What do I do for acceleration? I want the overall acceleration with a magnitude and a direction. Well, what do I do? Max answered it before, so I can call him again, but he already answered it for this part. What is it?
You should graph the velocity graph, like graph the velocities, and then use that to find it.
You might be saying, the idea you might have right, but you're not saying it. So just go to math for a second.
Because there's just horizontal lines because they're constant.
One's horizontal, one's vertical, technically.
I'm just the intersection point of them.
Come on, you guys are overthinking it.
Pythagorean theorem.
Pythagorean theorem. If you're given the components and you want the overall acceleration with a directional, always go back to Pythagorean theorem. It's the same thing we did up here earlier. This whole same concept, remember this gave us the velocity at an angle, right? Well, now we want to find what about the overall acceleration at an angle. So we could look at this acceleration as put a dot here. Well, the acceleration is negative 0.62 and it's positive 0.44. So if I want the overall acceleration, I'm looking really at this blue vector right here. Okay, that's the acceleration I'm trying to figure out, the blue vector right there. So again, if you're trying to find the acceleration as a magnitude and direction, simply take the components again. 0.62 squared plus 0.44 squared under the square root gives you the acceleration magnitude. Then if I want the angle theta, again, I'm going to do the tangent inverse of y over x. And I know my answer will absolutely be northwest. And I don't know that because of my theta answer. I know that because of the triangle I draw in here. I highly recommend whenever you're finding resultants that you draw the triangles. Draw the triangles. I know it sounds like it's like simple, but it helps you to recognize your angle theta and where it is and what direction it's given in. So that's my angle theta right there in the diagram. And I know that it's going to be north of west. This is west, it's north of that. So my angle theta here, whatever I get, I'm going to put northwest afterward. Okay, do we have numbers for those just so we have a value in case we want to write them down? Chip, what do you got?
For the angle, I got 35 point, I guess you'd say 4 degrees.
Okay. And the magnitude, what was the magnitude turn out to be? 0.76? 0.76? Okay, so again, this acceleration of negative 0.62i and 0.44j just simply means that you're feeling different acceleration in the x than you are on the y, but this is the overall acceleration felt right here. It's 0.76 and you're feeling it at an angle of 35.4 degrees. And this is not going to change the entire problem. Okay, it's not going to change because again, the acceleration in this problem is constant. The acceleration in the x and the y do not have a t component to them. They are constants.
Oh, so if it wasn't constant, you'd be finding it at like a specific time?
Precisely, Tristan. Very good. You would take again, you would have to say to yourself, oh, there would be a t here. There'd be a t here. And I'd say, find the acceleration at 18 seconds, right? You plug the 18 in for t in both spots. You get values for acceleration, whatever those are. Then you would use those values to do this. But because these values are never going to change, I know I can use those no matter what time I'm looking at. Okay, but it depends on the time it's actually asked about. Again, average acceleration, do the math if you want, you'll still get those two numbers for average. I'm obviously going to stop for today there. We're not going to get to 4-4, which is fine. I don't mind 4, 1, 2, and 3 today. So what I'd like you to do, if you take a look at your homework for this, just to kind of reiterate, am I up on here? Yeah. Here's the homework so you can get an idea. So this was what was due today. This is where we are right now. This you turned in today. Okay, so I made this homework for 4-1 to 4-3 not due until the 22nd. It doesn't mean you can't start it tonight. It absolutely doesn't mean to wait until the 21st, obviously. Okay, this is a little integral and derivative packet for review. This will definitely help you if you practice this for the quiz that I'm going to give you guys on Friday. I would recommend it again. I put it due on Friday for that reason. Then I'm going to give you, and this is already in the documents and handouts right below, one-dimensional, so back to 1D, so we see a little review, all three response examples to practice. Then again is when the homework is due the following day in class. This is not due in class. It's due on a day I don't meet you, which is why it says 8 a.m. Okay, so you're going to see a lot of homework things there. Please start filling this stuff out on your agenda and make sure you're pacing yourself time-wise. I personally think it's a good idea to start 4-1-4-3 tonight or tomorrow. I know that this is also due on the 18th, so you don't have to do all of 4-1-4-3, but just to give yourself a little bit of practice when it's fresh in your mind, maybe start working on those for the next couple of days. Okay? I have office hours today. I'm going to be here, so if you want to hang out and do work in this room, even if you have no questions, you just want to do homework somewhere, it's a good room. It's very conducive for learning because other people are going to be doing the same thing. So if you need a space to work and want to work in groups, hang out. Work.
Are you going to be here tomorrow?
Yeah, for science and Olympiad from 12 to 4 in this room. So if you want to come for help, just have a place to work or come ask questions, you come out tomorrow.
Okay. Because I haven't taken class right now, so I can't say now, but
Yeah, 12 to 4 tomorrow. The SAT should be out around 12. I'm the proctor for the second half, so I'll be coming by as soon as it's over. So if you get here at 12 and I'm not here until 12:05, just hang out.
Okay.
Okay?
Alright, thank you, Scott.
So this is the position function. This is the position function.
Yeah.
So that's, well, what this is giving you is actually the position.
So I had to,
So this is the
ask
X
during the
position,
class,
right?
instead of
And
waiting.
this is the Y position.
That's
So
one
this is
lesson.
giving you.
Get a free?
Yeah, I was just doing it on the other thing.
So you're trying to get the angle for this one also, by the way?
Yeah, I realized that.
That's okay. The only issue you're going to run into is that as long as your table is the right set. So let's see what the different life here is. What's going on? One second, one second. Nice. Yeah, this is great. So,
And I know how to do this.
so this will be the X position, the Y position, the overall position. So if you go X and Y for all my hypotenuse, that's exactly what it would be. And that would be the angle. This is a great idea. You guys should all do the same thing. It's a great idea. And that's all for position, right? So there's actually what I'm going to show you guys. You're probably learning the
Well,
calculus.
if you just put equals equation
You don't even need to actually. You can use a function called
and just
integrate.
press insert.
Yeah, is that what for? Nice. You're gonna have yourself in calculator and just learn some around there.
I kind of figured out.
Awesome. So I think it's really technically group 6. But this is gonna go to the graph actually. We want to end with which is in math. It's in math.
Give it that,
And
and
then
then
derivative and derivative. And then it has to be also.
just plus
So
x.
I meant to put that in Y4, not the first one. Get rid of that.
Oh, yeah.
Oh, no, I don't want to go away. Alright.
Okay.
Well, you can do it. Yeah, alright.
Let's see. 0.1 times x.
Square root.
And then goes plus 7.2.
You got it?